Welcome to Definite Integrals Part 1, Riemann Sums, where we continue the pre-work of calculus. Riemann was a German mathematician, and he was figuring out a way to add up basically rectangles to approximate the sum of the areas underneath a curve. Alright, at first he would divide, he'd look at a curve and then he would divide it up into subintervals. In this case it's 2.5. The width of each rectangle is 2.5. In this case the width of each rectangle was 1. And the idea was to continually make these rectangles smaller in width so that eventually you would use a limit and make it go to 0. Okay, so what we're going to do is we're going to make the width of this rectangle D and the width of this rectangle D. We're just going to call the width of the rectangles D. Alright? So, the area underneath the curve here is the width times the height, which would be the y value, f of x sub 1, plus the width again, same width, times the height of the second rectangle, f of x sub 2. So Riemann sums is always about finding the area of rectangles. In this one, this is going to be ridiculous. That's okay. D times f of x, f of x sub 1 plus D times f of x sub 2 plus D times f of x sub 3 plus D times f of x sub 4 plus D times x of x f of x sub 5. Okay, I think that's why we need to use sigma rules, because this could get really monotonous, especially as you made the width of these smaller and smaller. Okay, let's go ahead and organize our thoughts a little bit more. Are you ready? Alright, go ahead and write that down. Alright, now we're about ready to use sigma notation to create a formula, and here it comes. Let us create a sigma formula to represent this. Alright, the summation k equals 1 to n of D, that would be the width, times f of x sub k. And remember, one of our properties of sigma is to move the constant out front. So the width times the sum of all the heights of rectangles. Okay, and here is the fundamental theorem of calculus. The integral from a to b f of x dx equals the limit as d approaches 0, the width approaches 0, of d times the summation 1 to n f of x sub k. Alright, so now we are going to use this formula right here to approximate the area under a curve. Here is your setup. I'll let you get some graph paper out. I have already graphed x squared, and we're going to try to find the area underneath it using a left-hand Riemann sum, a right-hand Riemann sum, and a midpoint Riemann sum. And right now, I'll let you copy this all down, and then I'll come right back. Alright, I know you've been asking yourself, while you were copying this down, what's a left-hand Riemann sum, a right-hand Riemann sum, and a midpoint. Yeah, we'll talk about that right now. So first of all, let's go ahead and divide this up into some sub-intervals of equal size. So b minus a, 2 minus negative 2, divided by 4. So that's 4 divided by 4. So d is going to equal 1. So my subintervals, okay, my bounds are going to be negative 2, negative 1, 0, 1, and 2. Okay, the left-hand Riemann sum will use those 4 values when evaluating the Riemann sum. The right-hand Riemann sum will use these 4 values, negative 1, 0, 1, and 2. And the midpoint Riemann sum is going to use the midpoints between each of these. So it's going to use negative 1.5, 1/2, sorry, negative 1/2, 1/2, and 1.5. So left-hand Riemann sum, it's going to be d, which is 1, on the outside, just like d's on the outside here. Alright, f of negative 2 plus f of negative 1 plus f of 0 plus f of 1. So 4 plus 1 plus 1 plus 4. Oops, no, f of 0 is 0, you idiot. And then f of 1 is 1. So my left-hand Riemann sum is 6, because it's 1 times the sum of 6. The right-hand Riemann sum, again, the widths are, okay, the left-hand Riemann sum, I'll show you which rectangles we just added up. That rectangle, that rectangle, this really super skinny rectangle, and then this rectangle right here. That's what we just added up. The right-hand Riemann sum, we're going from the right-hand direction, so we're going to grab that one, that rectangle. We're going to get this rectangle right here. We're going to get this skinny rectangle right here, and then we're going to get this rectangle right here. So the width again is 1, and that would be f of negative 1 plus f of 0 plus f of 1 plus f of 2. So f of negative 1 is 1, f of 0 is 0, f of 1 is 1, and f of 2 is 4. The right-hand Riemann sum is also 6. And then we can also do the midpoint. So f of 1.2, right about there, that rectangle, f of 1/2, which is right about here, it's going to be this little bit, and then f of positive 1/2 right there, and then 1.5, looks like it's right about there. Those are the ones that we're going to be adding up. So the midpoint, the widths, they're still all 1 times f of negative 1.5 plus f of 0.5 plus f of sorry, that should be negative 0.15, negative 0.5, 0.5, and plus f of 1.5, close parentheses, so 1. Negative 1.5 squared is 2.25 plus 0.25 plus 0.25 plus 2.25 for a grand total of 5. And I think if we actually did the integral, the actual total would be 5 1/3. Nope. Actually, it would be, let's see here, yes. If you actually did the integral the way we've already done definite integrals, we'd find out that it was 5 1/3. The midpoint Riemann sum is, I've never seen it where it hasn't been the closest approximation to what it is in reality. And remember, we've done things backwards. They were trying to get to 5 1/3, not knowing that it was 5 1/3, because they did not yet have this whole integration thing. They were just trying to come up with a formula for the integration thing there. This does conclude Definite Integrals Part 1, Riemann Sums.